keep track of such things, there's a good chance we'll get through this part today because there are lots of tables. So in Unit 5, there's no Unit 5 exam, but there will be questions on your final over this stuff. Okay, so the chaos, chaos, whatever, that's entropy. Chaos and entropy are kind of, actually, chaos, entropy, disorder, they're kind of synonyms. So these might be kind of some familiar terms. When we talked about thermodynamics back in Gen Chem 1, we talked about like for instance, Q is equal to MC sub P delta T, those things. Tracking changes in thermal energy. We talked about these terms. Okay, if you have a reaction occurring in a beaker, that is your system. And then anything outside the beaker, actually including this headspace here, anything outside the beaker would be the surroundings. Okay, and your system plus your surroundings is equal to, guess what? The universe. Some universes are larger than others. Okay, so that's kind of how it goes. The system of interest, the thing that's outside the system, the surroundings, and the universe is both of them together. So even the title of this, doesn't this sound big? 2 fundamental laws of nature. Doesn't that sound awesome? 2 fundamental laws of nature. Okay, that are important in thermodynamics. Okay, they are both kind of the getaway. They're like getaway. So dispersion, getaway, dispersion of energy means basically things want to take the energy they have and share it. Dispersion of energy. Okay, things just tend to do that. And things, I should say systems, tend to want to disperse their matter too. Dispersion of matter. Okay, so if you have a system that wants to dissipate its energy, that system also wants to take its matter and spread it through over the universe. Okay? And the whole dispersion of matter, we call that disorder. And it kind of reminds me of my house. Right after I clean up my house, it's like things are where they're supposed to be. And then it's what we call entropy sets in, or chaos or disorder, and those things throughout. And I'd love to have like a time-lapse video kind of showing those things relocate to someplace else. That's just the way things happen. So we're going to talk, I'm introducing it now, but we'll be talking more about something called spontaneity. And if somebody is spontaneous, or if something happens spontaneously, it means it happens just without any provoking or whatever, okay? So there are certain reactions, certain processes that occur spontaneously. And if the way nature is, if nature wants to get rid of its energy, and if nature wants to disperse its matter, okay, by golly, if you have a system that's doing both of those things, that process that system's undergoing is what we call spontaneous. It's spontaneous. It's like falling down a hill, okay? So we'll be talking more about that. So state function, we talked about state functions before. The opposite of a state function is a path function versus path function. Whoops. Okay, so path function is one that does depend upon path. State function does not depend upon path. It's independent of path. And I think the example I gave you when we covered it earlier in general chemistry was your bank account. So, like, if you're at 500 now, and your mom or your folks are like, cool, that's 500, it means you only, because you had 600. Not to mention that you started with 600, you dropped it down to 400, you added 200, you dropped it back down to 300, okay? But you have 500 now, okay? So it only depends upon the initial and the final state. In the case of your parents, you went from from 600 to 500. Your delta cash was $100. I don't care how it came about. Okay, so it's a state function. So entropy, okay, entropy is a state function. It does not depend upon path. And entropy is a feature, it's called a thermodynamic property, entropy. Remember, entropy is the disorder or chaos something has, entropy. It's a measure of the disorder of a system. In other words, the entropy in my house after I clean it up is low. The entropy 2 weeks later is high. It's increased disorder. It's got a positive change in entropy. So one of the things, your homework that's for Friday, is you're going to have to be able to kind of look at a system and say, does that look ordered or does that look disordered? And we're going to look at some examples what that means. Okay, but in general, the entropy or disorder of a system is associated with the energy within that system and how it's distributed on a small level. So the greater the disorder, the higher the entropy. And I'm going to go ahead and let the cat out of the bag. We're going to use the variable capital S for that. So the greater the disorder, the higher the S. Okay. So entropy can be associated with, like you've read, randomness. The term chaos is great for entropy. In general, we think of it as the dispersion of matter. Symbolized with the capital letter S. I guess I wasn't too far ahead of myself. So we're all about making sure we use, there's no naked numbers in this class unless it's pH, right? pH, there's no units. A case, there's no units. I guess there's a lot of things that have no units. But entropy has units, and it's units of energy, energy per mole, absolute temperature Kelvin, or energy per Kelvin, if it's the what we call the total entropy of the system. Okay, so entropy. Now, entropy change. We've talked about a lot of changes here. The symbol for change is a triangle called the letter delta. So delta S is entropy change. So the change in entropy. So you can kind of think, again, of like picking up your house. What was the change in entropy?
And again, it may well be. It's a lot.
He looks like he's having fun. So see if this looks familiar. Maybe, maybe not. I guess it wouldn't look familiar. What should look familiar is Q. Because in general chemistry, I think Chem 1, do you remember this? Q is equal to M C sub P delta T. Yep. So Q actually is change in thermal energy. Okay. And I'll go ahead and tell you something we're going to hit in our notes. We said that if the pressure is constant, if, I'll just put P for pressure, is constant, then, and I'm going to have to write above it, Q is equal to delta H. Change in enthalpy. Oh, now we get to one of my pet peeves. Enthalpy. Entropy. See how similar they sound? They're both thermodynamic properties, too, characteristics. Okay? But enthalpy, entropy. So, if you want to know the change in entropy that your system has undergone, you can track the change in thermal energy divided by the temperature. But be careful. T is Kelvin scale. So these few slides might help you with your homework for Friday. And these kind of make sense if you visualize them. So for instance, let's say you have a substance that is in its liquid state and a substance that's in its solid state. Doesn't it seem like on the molecular level, in its solid state, it's moving less? So actually in its solid state, it has less entropy. Okay, so put another way, if you were going to go from a liquid to a solid like that, kind of from left to right, that would be a decrease in entropy. Decrease S, okay? And your delta S, your change in entropy, would be negative. That's kind of the convention you need to start to kind of think about. Delta S would be less than 0. And liquid to a solid. I bet you buy that. And the same thing would be if you're going from, let's see, liquid to a solid, a gas to a liquid. Okay, decrease in entropy. Here's another one for you, and I have an example coming up. If you have several compounds and they are closely related, and the example we're going to look at are kind of a set of hydrocarbons, only carbon and hydrogen in them. For the larger one, doesn't it look like it's more potentially chaotic? The larger the molecule, the more entropy that molecule has. Okay? So the smaller the molecule, the more ordered it is, the less entropy it has. Remember, entropy is disorder. Here's one for you. And again, if you kind of picture what it's, and I have some pictures coming up. Let's say you're going to take a solid solute and you're going to dissolve it in a liquid solvent. Okay? Can you see where that solid, that now used to be a blob, now it's dispersed in a liquid? Doesn't that seem like there's more entropy? More disorder? Yeah. Okay, so increasing entropy there. This is another good one. Remember, not all solutes need to be solids. Let's just say you take a gas, like you're going to make some pop, and you're going to take carbon dioxide gas that has its mind of its own, and you're going to confine it to a bottle of pop. Okay? So basically, you have taken something like this, and you have narrowed it down to you have actually decreased entropy. Okay? Decreases when a gas is dissolved in a liquid. So those are just kind of eyeballing things. Now here's one for you. We talked a little bit about if you have an ionic compound, basically you have a cation and an anion that are stuck together with an ionic bond. And the weaker the bond, because they're not all the same, okay, it's like a Coulombic, like a negative positive sort of attraction. The weaker this attraction, the more entropy there is. That kind of makes sense. If it's really strong, okay, then it's less entropy. Weak, more entropy. Okay? As the attraction between ions and ionic solid decreases, entropy increases. So here's some pictures to kind of go along with what we were talking about. We have a phase change. These are the top two are phase changes. Something goes from a solid to a liquid, increasing entropy. Okay. Something goes from a liquid to a gas, increasing entropy. This was where you're dissolving a solid solute, doesn't look like a solid, into a liquid solvent. Okay. These were all nice ordered here. This is increasing entropy. All these are increasing entropy. Okay. So you look at the system before and the system after. Is there more disorder? More randomness? Yes. Then it must be increasing entropy. So this was the example where I said several hydrocarbons, and kind of the bigger one has the greatest entropy. Finally, we actually have some entropy values you can sink your teeth into. Okay, the standard molar entropy, that's what that little circle means. Do you guys remember when we talked about standard molar enthalpies? Do you see the problem here? Okay, the H knots. Okay, these are standard molar entropies. So notice it gets bigger as you add more carbons and hydrogens. Entropy. Whoa. So I'm going to kind of hit briefly the laws of thermodynamics. Doesn't that sound important? This one is like, this one totally, I'm like, duh, right? Who came up with this? And it's almost like a math thing. Remember is it the commutative property of math? I'm not sure. But it says, if body A and B are in thermal equilibrium, okay, and there's a body C, okay, oh, no, wait a minute. Body A, B, and C. If body A and C are in thermal equilibrium, and if body B and C are in thermal equilibrium, then body A and B are also in thermal equilibrium, okay? That's what they're saying there. That's wonderful. The first law of thermodynamics says something, and this is kind of, remember these diagrams? This must have been at the end of Chem 1, because I kind of remember this. If this is our system, remember we kind of talked about different scenarios with energy and work done to or by, okay? And basically what this is saying is that the internal energy of the system increases when energy is transferred from the surroundings. This is the surroundings, remember right here? Energy is transferred, no kidding, right? So I think we call that, maybe was it delta H? Might have been a Q term, I don't know. Okay, but if we're adding thermal energy, or remember the W term, if work is being done by the surroundings onto the system, in both of these cases, the internal energy would increase. I think that's U. I mean, you're like, duh, right? That so makes sense. All right, now this is something like we just have been talking about. The second law of thermodynamics is in regards to entropy, chaos, disorder, randomness. Okay? So talking in regards to the universe now, which is what? Two things. It's the system and the surroundings. Entropy of the universe will always increase. There's that word spontaneous again. The entropy of the universe will always increase for spontaneously occurring processes. For a spontaneously occurring process. And that goes back to what we said, the laws of the universe. It's like they want to disperse energy and they want to disperse matter. Okay? And if they get to do that, we call that increase in entropy. It's like rolling down a hill, and it will be spontaneous. Falling out of bed, rolling downhill. One more law, and I don't think we're necessarily going to use this. In regards to entropy, it says if you have a solid, perfectly pure, solid crystalline substance, okay, the entropy, S0, at negative 273.15 degrees Celsius is 0. So my point here is that's a really cold temperature. Oh, wait a minute. You know what? I shouldn't do that. I'm going to have to erase my knot, because by definition, what that knot means is 25 degrees Celsius. So let me take that knot back. Entropy of a pure substance, the randomness, chaos, okay, is 0 at absolute 0. So that could be helpful. All right. So the second law of thermodynamics said that the entropy in the universe is increasing for spontaneous processes. Entropy in the universe is increasing. Delta S universe greater than 0. Yeah, that's what that says. But remember that the universe is composed of both the system and the surroundings. So in order to really track what the change in the entropy of the universe is, you have to add the change in the entropy of the system and the change in the entropy of the surroundings. Okay, is this kind of starting to look familiar? Because there's going to be something that looks very familiar coming up. So switching from the universe to the system, because that's more practical. The change in entropy of the system, the little system of interest, your beaker, the change in entropy that's occurring there. We can simply, if we look at its final state, and since it's a state function, we can just compare its final state, and from that subtract its initial state. Deltas are always final minus initial. Okay, and we can get the delta S for the system. So now doesn't this look familiar? Remember delta H naught is equal to summation of A H naught products minus summation of B H naught reactants. It's a very similar thing, but we're not going to do one of these today, or one won't be due for your homework for Friday, but we're going to work through one. So now instead of change in enthalpy, delta H, we're talking about change in entropy. But those that A and B are the same thing they were before. They are the stoichiometric coefficients. And where do we get our S naughts from? We get them from tables. So the naught means standard state entropy. And so we need to remember what standard state means. So when we talked about it before, so this right here, this is the naught. I'll put a little circle there. That's the naught. That's what the naught means. It means the temperature is 25 Celsius, the pressure is 1 bar. This is going to come in handy when we talk about electrochemical cells. The fact that what that naught also means is that if you have an aqueous solution, they are 1 molar. Cool. All right. So the change in entropy of a system. Now, this actually, I know what I should say. Not for any system. That's what was different. It's actually for a chemical reaction. All right, so we're going to do an example. And so in order to do this example, these might come in handy. Some standard molar enthalpy. Oh, dang it. See, look at that. Is that a typo? Are we all looking at the same typo? See, this is why you think that should be entropy? Well, it better be. So anyway, the more I teach this, the more I'm like, really? Is that what I meant to say? Okay, so we can use these in that summation equation. So let's do this one right quick. Okay, so we have 1 mole of methane reacts with 2 moles of O2 to form 1 mole of CO2 and 2 moles of H2O. And we can use that summation formula to knock out the entropies. Okay? And once we get an entropy, if the delta H, I should say to change in entropy, if the delta H is positive, it's creating disorder. If the delta H is negative, it's creating order. Okay? So is the system becoming more ordered? We would look for delta S less than 0. Oops. Yeah, delta S negative. Okay, if it's becoming disordered, we're going to look for delta S greater than 0. Yep. All right. So from that table, I think a few slides ago, these are all on that table. These are in units of joules per mole Kelvin. So we're going to use these in the problem. You won't have one that's due for Friday, but you might for Monday. So remember how you work these. You just have to kind of keep your wits about you and make sure you show all of your work. So if we focus on the products of CO2 and H2O, okay, we need to bring in the stoichiometric coefficient. So and you have to show all of your work. So on the product side, we have 1 mole of CO2. That is the S naught, the standard molar enthalpy, entropy, standard molar entropy for CO2. Plus, then we need to look it up for water, plus 2 moles of H2O times its S naught, 69.9 joules per mole Kelvin. Notice that moles are going to cancel here. We'll be left with units of joules per Kelvin. And what I would do is do this, okay, and set it aside and then start another problem for the reactants, summation for the reactants. So you get 353.5 joules per Kelvin. Then we do it to the reactant side. So there was methane, 1 mole of methane, 1 mole CH4 times 186.3 joules per mole Kelvin. And then all we need is the oxygen plus 2 moles of O2. And then from the table for O2, it's 205.1 joules per mole Kelvin. And then ready to knock that out. And you should come up with 596.5 joules per Kelvin. If you do it this way, you have a fighting chance to make sure you get the last part right. So we're going to take the first number and subtract from it the second number, right? So the change in entropy of the reaction is 353.5 kilojoules minus 596.5 kilojoules. If you do it this way, you're likely to get that last step right. And clearly we have a negative delta S, a negative change in entropy, okay? So it's creating order, exactly. And like I said, for Friday, you don't have to, homework, you don't have to do any of these, but, so it's creating order. So exactly. Whoa. Which we'll talk more about. There's another thing that decides whether a reaction, chemical reaction as it's written, is going to be spontaneous. But this in and of itself does not look like it's spontaneous, does it? Right. Exactly. All right. So now we have a bunch of tables. And so we're going to look at a couple at the beginning, and then we're going to look at the things at the end. Now you're going to see 3 columns on these tables. Okay, the last column is what we've been talking about. Okay. The other columns, let's see. Oh, yeah. We talked about this one before, too. Standard molar enthalpy of formation, that's the H naught. Actually, as much as I tease about enthalpy and entropy, we are going to have to talk about enthalpy again coming up, the H. Now, this other one's kind of neat, the standard molar Gibbs free energy of formation. I hear that if you're in biology or biochemistry, that you need to use that one. And that actually is a capital G. All right, so here we go. See the 3 columns, the enthalpy, the Gibbs free energy, and the entropy. All right, that's for aluminum. And these go alphabetical, so of course aluminum, barium, beryllium. So hopefully you can find what you need on these. Oh man, I thought I hid this. All right, well, it looks like we're going to, skip several slides. I thought I did. Okay. So if you go clear to zinc, right? Then the next slide after zinc looks like this. And we've got 2 slides of organic compounds. Of course, organic means that it's got carbon and hydrogen, maybe throw in some oxygen, nitrogen, organic compounds. And then this one is also. But be careful because it's possible, I think these are pretty laid out, but it's possible that for 2 different compounds to have the same formula, but you'd have to go by the name to make sure you have the right one. Okay. Well, you're like, well, why would you skip all of those? Well, because we're getting to the assignment slide. So now, notice how this is different. This is the change in entropy, not of the system, but the surroundings. Okay. So, let's see, I look down here. If it's occurring at constant temperature, if you picture what the system and the surroundings relationship, basically whatever change is, it has to be a net wash. So if you focus on this and this, it says basically what your surroundings change in entropy, the opposite will occur with your system. That's what that's saying. Not to mention the universe is increasing entropy. But, all right. So let's take a look at these. These will be due on Friday. No calculator required. But be careful, there is just a little bit of explaining. So here's my hints for these. Okay. So for this one, basically they give you A, B, and C, and it's kind of a common thread in these. Indicate whether there will be an increase or decrease in entropy and explain your reasoning. So if you have time to look at them, you're going to see that the first one is a phase change, the second one is a phase change, and the third one is a phase change. Oh, no, third one's not a phase change. The third one is combusting fuel. So just do your best. You think there's increasing or decreasing entropy, and why? Based upon what we talked about.
Okay, at the top of that one.
Hang on, let me go back.
You said if it's delta S is greater than 0, then the disorder is increasing, right?
Disorder's increasing.
Okay.
Yeah.
Okay, I just want to double check that.
Yeah, it's good to, because this is helpful in the rest of part 5,
Okay,
or unit 5.
I just want to make sure I have that right.
Yep. And order is, I put order is increasing if it's negative.
Okay. I
Yep.
just wanted to double check. Just to make sure I have that right.
Sorry.
Sorry.
Yep, that's cool. And then these you have in A, B, and C also. And again, these are worth, you should take the time to do these. So you get that homework credit. But let's see, keep an eye on what the phase is between the two. Okay, so you see kind of the reaction arrow showing you the different states. It's going to this state, starting from this state. Pay attention to the phase and the pressure. Oops, was that my only hint? I think you guys are okay with that. And it says arrange, oh, I know, duh. It says you're supposed to arrange them in order of increasing change in entropy. So getting more and more disorder between the two. The next one is this one, and it's got 4 parts. What's my hint here? Oh, I guess I didn't have a hint. I think you guys are kind of seeing the pattern here. Indicate whether entropy would increase or decrease. Have a 50-50 chance, right? This one doesn't ask it. Well, it does say explain. Oh, it says if you can't guess increase or decrease, then you need to say you don't have enough information and why. And then this one. A, there's a difference in phase change. B, there's a difference in amount. C, there's a difference in phase change. There's a phase change and temperature change, which shouldn't be too surprising. And D is just a temperature change. So again, kind of left and right. Think of the right one as the one you're going to end up with. Is it more disordered or less disordered? More entropy or less entropy? For each of these, indicate whether delta S should be positive or negative. And then it's kind of like we said. Delta S's that are positive means that disorder is increasing. Delta S's that are negative means that actually disorder is decreasing or order is increasing. So, all right, I'll push those out there. We might have a busy study session today.
Yeah, I was hoping we'd get out of class early so we could steal you longer than the other kids.
Oh, yeah. Yeah. Which is the case. I forgot to tell them that there was a study session.
Oh, a couple of them already said they're going.
Okay. And And my car is red, not yellow.
Oh, really?
So, yeah. So no bingo or whatever.
Laura, happy about it?
Yeah, I'm happy. I think it'll be a good color. It's a new car. Who couldn't be happy with a new car, right?
I don't know, I like my car, and it's getting kind of old.
What color's your car?
White. Doesn't show dirt.
Well, the important thing is you like your car.